Hello everyone, my name is Shanmuk and today I am going to present our project titled as Income Classification using Genetic Programming. This project was done for the evolutionary algorithm models, and in this presentation I will walk you through these datasets, our methodology, the GP models, results and key insights. Let's coming to the introduction. The main aim of our project is to classify individuals in two incoming groups, whether they are earning more than $50,000 or less than $50,000 or equal to $50,000. And the dataset that we are using, it is a modified version of AdolSense dataset, and it is a mixed version of numerical features like ages and hours worked per week and capital gain, and also categorical features like occupation, education levels, and work class, and all the stuff. One of the key reasons that we are using genetic programming is because it is interpretable and symbolic models. Unlikely, it is a neural network, and the GP model can be read as mathematical expressions, and it makes easier. And so that's why we choose the GP. And in this project brings together the features of engineering, pre-processing, evolutionary algorithms, and explainable machine learning mainly. And coming to this, most of the people don't know about the GP. We are going to this, what is genetic programming. This is a evolutionary algorithm program inspired by natural selection. It is like biology and all the stuff. Instead of learning weights like neural networks, GP evolves actually computer programs and mathematical expressions. Every model in GP represents the tree structures. The nodes in the trees can be mathematical operators like addition, multiplication, logical operators like add, or, and conditional operators like if, then, else. That's all. Most of the stuff would be like mathematical. And GP improves solutions like using three core operations like selection, crossover, mutations, and these are all the stuff mostly in the GP. Our multiple generations, the GP program evolves and gradually produce better solutions. GP is especially powerful for classification tasks that requires interpretability. And coming to the dataset overview, our dataset is based on the well-known AdolSense dataset. It contains around 39,000 training samples and 9,769 test samples. And in this, especially, we are using 14 original features describable demographics, education, work experience, and financial attributes. The target variable season binary 0 represents income is less than 50K and 1 represents income is greater than 50K. One of the challenge with the dataset is classic imbalance. Most individual belongs to the lower income group. So we need to design the model carefully to avoid biased predictions. The dataset also includes the category variables with many levels, such as occupation and native countries. Another issue in this presence of missing values represent as the symbols question mark, which most of the people use it as the question mark, so we are also using the question mark. We addressed these issues during pre-processing. And coming to this features engineering. This is the main thing we need to discuss because this is a lot for our to improve model performance, especially for GP. We created more than 14 new derived features. Some important engineered features including age, education, work related, financial, and these are also. Each and everything we have so many of things. First is age square to capture non-linear income partners, Iseng to highlight early career people, is prime age to identify peak earning age range between 35 to 55. And coming to education based, it is in a high education. It's indicating education num greater than or equal to 13. Has college for bachelor's and master's, and work it is more than 40 hours or less than 35 hours, and financial and all the stuff. And coming to interaction features, this is like a little bit of calculation like critical for GP. And as I said before, GP is only on mathematical stuff, and this is all stuff. And like all the stuff you can see over there, those are all multiplications, and these interaction features are extremely useful for because GP can be built more meaningfully expressions when the data is already contains information relationships. And next one is data preprocessing. To prepare the data for modeling, we follow the structured preprocessing pipeline. First, we replaced all the occurrence of question mark and none, all this stuff. And next, we filled missing categorical values with the mode of each column, the filled numerical missing values within the median. Then we applied so many minimum maximum scalings. It is range of 0 to 1. Since our dataset contains many category variables, we used one hot encoding to convert each category into a binary feature. Finally, we ensured that training and the testing has identical features columns and transposed the matrix, so that's why GP could evaluate all the samples vectorized. And coming to these are all the symbols you can see that mostly we are using in primitive sets. First one, I'll go with arithmetic. It is like I think you already know before addition, subtraction, protected division to avoid divided by zero errors. And mathematical, it is a square roots, algorithms, natives, and logical and or not, and comparison operatives like less than or greater than, and conditions, conditional operators like if then else, structured, allowing GP to create rule-based logics, and random constants like -1, 1. These are the rich primitive sets give GPs the flexibility to evolve very complex and expressive models. And coming to the next slide, my friend will continue all this stuff. Thank you.
Hello everyone, I'm Sangamitra and thank you Shinmukh for handing on me. And I'm gonna continue with slide 8, which is GP configuration. We have configured the GP algorithm with parameters that encourage both exploration and exploitation. A population of 1200 individuals that gives us enough diversity, and 150 generations allowing long-term evolution. And we have taken the crossover probability of 0.85 and mutation of 0.12, and we selected the tournament selection with a size of 7 and a maximum tree height limit of 15 to control the bloat of the tree. And we created a Hall of Fame storing the top 15 best solutions over the entire run. These hyperparameters were chosen based on experimentation and need to balance complexity. And coming to the next slide, here we go with the fitness evaluation. For fitness evaluation, each individual GP tree is compiled into a Python function. This function is then applied vectorized across all training samples. If the output of the tree is greater than 0.5, it is classified as income equal to 1, otherwise income equal to 0. Fitness is calculated using accuracy, which is simple and effective for binary classification. Protected operators prevent crashes due to invalid operations like logarithm of negative values or division by 0. And coming to the next slide, evolution progress. The evolution process showed clear improvement over generations. In the first generation, accuracies ranged between 0.61 and 0.75. As generations progressed, GP gradually learned more meaningful expressions. Around 20 generations, we saw rapid progress, and by 120 generations, accuracy started stabilizing. Our best model achieved 0.8513 training accuracy. And coming to the explainability, like what GP has learned from the code, we have examined the evolved trees. We observed several human-like patterns. For example, higher education level correlates strongly with higher income. People working long hours generally have higher income. Capital gain is one of the strongest predictors. Part-time workers are more likely to fall into lower income group. Married males with professional jobs tend to earn more. And this shows that the model not only performs well but also learns meaningful rules. And coming to the limitations, while GP performed well, it does have some limitations. We observed some limitations. Those are trees can grow too large, making interpretation harder, and we can call it as bloat. GP requires significant computational time, especially with large populations. Performance gain slow down after many generations, and GP can get stuck in local optima if diversity decreases. And coming to the conclusion, to conclude, our project successfully built a powerful and interpretable genetic programming model for income classification. We achieved about 85% accuracy, and our model learned several intuitive and meaningful patterns. Feature engineering had a major impact on performance, and GP symbolic nature allowed us to understand how decisions were made. Overall, GP proved to be very effective method for mixed type classification problems. Thank you for listening. I'm happy to answer any questions.
Thank you.
Thank you.